talk of this session, Ryo Suzuki is going to be discussing the fine counting of anomalous dimensions.
Thank you for the introduction. My name is Ryo, and I talk about basically fine counting of anomalous dimensions. This is based on the work I published last year when I was in Sao Paulo. This is also related to the work which I did with Cinderella Kuran and Yusuke Kimura. Now, the quantity I'm interested in this one, the partition function, which is similar to the topic the Masanori just talked. And this the partition function is z of the n equals positive binomials and defined on S1 cross S3. And the range of S1 is beta, and the range of S3 is set to unity. And then we have a chemical potential mu. And then there are another two parameters, the theory NC, run for the gauge group, which is mostly UN, and the foot coupling. Now, this quantity is very similar to the what Masanori just talked, and I want to discuss what is this S1 cross S3. The difference between S1 cross S3 and this R3 is recognized when you put color charges. Because on S3, because of the passing error of the gauge fields, you get the Gauss law, and if you put one colorful charges on the North Pole, it should end on somewhere. So this is the reason where only color singlets appear in this theory, and you basically get confinement. But this confinement comes from this Gauss law constraint. It's not related to the real confinement QCD, because real confinement can happen in R3 due to strong dynamics. But if you take large radius limit, this partition function should agree with this one, and this is one Masanori just talked. It's the origin of the three-quarter problem, and I talk about this one. But the formulation is very similar. This partition function of S3 has undergone through the confinement transition from Gauss law at finite temperature large NC is infinite. So it has from some confinement phase where degree of freedom multiplies, and at some temperature it goes up, and then when you plot log of z, it becomes order MC squared quantity, and after that it undergoes the confined phase. And this region, at least around this criticality points, should be described by Fourier oscillators. And this transition is called Hagedorn transition. The basic difference between QCD transition and this Hagedorn transition is that this transition is driven by the exponential growth of the density of states. So when you put energy E, it grows exponentially with respect to that. So the famous conjecture is that Hagedorn transition is related to confinement to confinement, which is in ADS-FT point of view Hawking phase transition, which is the transition where some of ADS space becomes black hole. So I got this plot where the horizontal axis is temperature, vertical axis is chemical potential. This is gauge theory results, tree level. This is gravity theory results, tree level and gravity. And people studied lots of this thing, but I get this plot from Yamada paper. So there's some continuous line of Hagedorn transition which I'm interested in. Now, I have some mathematical motivation to study this quantity. That is to sum over bed-under solutions. Now, if you want to compute some physical quantity given by f of mu, and u depends on bed-under solutions. And then if you take sum over all bed-under solution with proper multiplicity, you get capital F. So how to compute things like this? First of all, I want to discuss what is bed-unders. Bed-unders is some polynomial equations for, in this case, polynomial equation for variable u1 to um. And we also have to provide a length of spin chain capital L. So you solve these equations. There are lots of solutions for given L and M, and plug in here, and then you want to compute capital L. And this type of equations show up frequently in various sit-ups in superuniverse theories. For instance, in this example, where t equals 4, n equals 4, super MX is constant, we take large n limit, then the theory becomes integrable. Then I take f as pinching energy, so this is pinching energy. Then this capital F is related to the part of this partition function Z. Another example is two-dimensional n equals 2 super M theory discovered by Nicholas Chattershilly. In that case, we take f as a norm of beta wave function to the power of g. The beta wave function is the eigenfunction of the Hamiltonian of the spin chain, which is diagonalized by this beta and equations. The way to compute the norm based on this distribution of roots, and then take the power, then after that you get this capital F is related to the supersymmetric partition function on Riemann surface. This problem is mathematically well defined. However, we only know algorithm for doing this, but we don't have any explicit one-line formula for this type of questions. It looks very difficult to get this, and I want to look for non-integral methods to compute this. This one. The tool is the finite group theory, where we relate multi-trace operator tasks by permutations. Now this finite group theory has a very good feature, which is easily extendable to finite NC. But there is a disadvantage that this method is just applicable for perturbative question in GMUs. It's not like integral theories. Moreover, if you use this finite group theory, you can find that one-loop mixing becomes simple, but not yet diagonal enough. Still, this type of things are good for computing statistical quantities like partition function, which is related to the trace of mixing matrix, because trace does not depend on the choice of the basis. So, then I will jump into main results. Now, the partition function, I look at the so-called SC2 sector of the binomials under small lambda. I will explain what it is later, maybe. Then I expand the partition function in small lambda, and this is the first question. This M of Mn is related to the one-loop dimension of operators made up of MWs and MZs. And you can compute this capital F Mn explicitly in small x, small y expansion. So you have some numbers here and here and so on, and you can continue. Now, my finding is that this function is written as this placistic exponential of single trace generating function. So when I put Ft, it's a sum over all multi-trace operators. When I put St, it's just sum over single trace operators, and they're related in this way. Now, then I got some formula for this single place generating function, which is written by Euler-Torschen and greatest common divisor in this way. So that's the something I got. And if you look at this pole, location of the pole, this pole, it gives you the Hamilton temperature of this theory on SU2 theory. And if you look at residue of the pole, it gives you the correction to this Hamilton temperature TH. There is some known results, but the point is I introduced a fully general chemical potential X and Y. So that's what I did, and I want to discuss some technologies behind. Is there any questions so far?
Can you say what were those subscript 2 and 0?
And 0. Oh, this is 3 level. This is 1 loop level. And it continues.
I see. And X and Y were chemical potentials for what?
X and Y is, okay, here term Xm, Ym correspond to the weight where the operators have M, Ws, and Nz's. It's like a fugacity parameters.
I see.
Okay. Okay, let's. I want to do it slowly. Maybe it's a bit too easy for the professionals, but anyway. So there are three definitions of partition function of any possible superunions if you want to compute. The first one is based on the path integral. And then after the path integral over S3, you get some zero mode integrals, where U is basically an integral of zero modes of A nodes over S1. It's very similar to the Polyakov loop. And then you get matrix mode integral n by n. However, if you can do a radial quantization of the theory, then you have Hamiltonian formalism, where the Hamiltonian corresponds to the dilatation, which is the definition of radial quantization. And in this radial quantization, this Hooft coupling dependence enters only on this dilatation operator. So you can expand D in small coupling. Ji is other global charges of PSU224, and H you can take as Hilbert space of mergeless or singleton operators. And if you take lambda goes to 0, which is treatable, you just count operators appearing on the theory, singleton operators. Now, I want to define the number of length operators by some subtraction, NLP minus NL of NP, and this second term is finite n fractions coming from the antisymmetrization identity. So it is well known that if you antisymmetrize more than n indices, where variables go from 1 to n, it just vanishes. And this is the reason of finite n constraints. And then correspondingly, trivial partition function with zero chemical potential is split into this large n part and finite n part. The finite n part can be seen only when the length of operator is greater than nc. So this exponential is suppressed by exponential minus, this exponential parameter is at least exponential minus beta nc. So this is totally non-perturbed effect from 1 over NC expansion point of view. No, now in my computation I totally neglect this finite n terms, but because I want to take the large n limits in the end. But there can be subtlety, which I want to explain. And I don't know really the solution. Now, Hagedorn transition happens at a finite temperature only if n is infinite. This is some well-known fact. On the other hand, Hagedorn temperature is related to the pole of this partition function, so something has to diverge. And if you look at this summation, this, of course, the growth of this coefficient NL as L goes to infinity is important. Now, in order to say that I can neglect these things, whatever happens, the first term should grow as exponentially as expected, while the second term should stay finite. And I have never seen any proof of this conjecture, but because otherwise there can be an order of limits problem. Well, in my situation is okay. There can be any some order limits problem, but anyway, I have to neglect just until answer this point. I want to explain another thing, which is truncation to the SA2 sector. The SA2 sector, which I just explained, is the sectors made up of this one are two complex scalars W and Z of any possible superunions. But the entire theory is defined on PSU2/4. So if you define a matrix model formula, if you recall the matrix model formula for the partition function, this is written as some exponential of matrices, where this is adjoint character and then some theory-dependent function. This theory-dependent function really depends on the sector you want to find, and in the tree level, the full sector is given by this function. Now, what I want to do is truncate them to this SU2 sector, but introduce mostly general chemical potential. So now it's x plus y. So this becomes that. And I still want to claim that this, even after that, Hagedorn transition still exists, but the precise value of TH is different. So I want to say that I'm not losing some qualitative features, although quantitatively they are different. So that's the what I want to study, and I want to discuss the permutation basis. Now, there are several choice of operator bases in any possible polynomials. The most convenient one at large n is single trace operators because they are directly related to the integrability of the theory. And when you start talking about permutations, this is good for studying one-to-one collections. However, then you can take kind of Fourier transform from permutation to representation. And this representation basis, such as this restricted Schur polynomial, is good to study finite n regions because this purple region, some operators are not really independent from these operators, from other operators. But in this talk, I do not talk about representations, just talk about one-to-one collections. And I want to say some simple question. How do you count number of multi-trace operators made up of m w's and n z's? Suppose m and n equals 2, and what is the number of this? And you can think of it. The result is this one. There are 10 operators. There are 2 single trace operators. 2, okay, double trace, double trace operator is 1, 2, 3, 4. Triple trace operator is 3, and this quadruple operator is 1. So how to get this number? Now, in order to answer this question, I need to really introduce permutations. And this permutation can be done in general PS22/24 language. First, you choose the alphabet of n equals 4, capital WA, and this capital WA can be some derivative acting on scalars, derivative acting on psi, derivative acting on F, or then even no derivative acting on. And then given this W, you could take a tensor product of them and then take a trace over this tensor product space by twisting by alpha. Alpha is the permutation group element, so it's really this quantity. Now this summand is just a product of numbers, so there's a redundancy in this labeling. So you can replace small ai, capital AI, and permute it with gamma, which is another permutation element, and this defines the same operators. The claim is that this equivalence class, given modding out by these redundancy relations, just gives you the unique multiple trace operator. And with this claim, you have to check. In the SU2 sector, things a little bit simpler because I'm concentrate on just Wm and Zn. So the odd flavor indices just becomes 2 number m and n. Then the relabeling symmetry is just permutations inside Wm or inside Zn. So when I take gamma from Sn cross Sn, then there is no action on the flavor indices, and the operator just equivalent. So you have to classify the equivalence class of Sn plus n modded by Sn cross Sn. But you have to notice that this Sn cross Sn acts as adjoint, not as right coset, so the counting is a bit complicated. To do this, I define a function called delta function on the permutation basis, which is 1 only if the permutation element is identity on this permutation group. And you want to compute this. Okay, then I have to solve this relation, alpha inverse, alpha gamma equals 1. This comes from this equation, obviously. And how to solve this? You need to remember just 2 facts. The one fact is each permutation has a cycle length. And another fact is this cycle type is invariant under conjugation. Here's an example of S6. We take elements. One is just identity, 2, 3, transposition, and 5, 4, 6. Cyclic translation. And this cycle type of sigma is just 1, 2, 3. And this cycle type is invariant under the conjugation, which can be easily seen by identity of this type. So if you conjugate by alpha, this doesn't change the cycle type, but it commutes the elements inside the cycles. Now my writing or notation has redundancy, because when I say 1, 2, 3, it's permutation of this. It can be 2, 3, 1, or 3, 1, 2. Similarly, if you have a permutation of the same length, 4, 5, and 6, 7, it can be written as 6, 7, 4, 5. Now you have to count this redundancy carefully, and then you get the number of solutions to these equations. And I don't really discuss what the number I get, but this is where you get. And assuming that we have a formula for NMN based on this counting, we can get a three-level partition function of n possible superelements in SU2 sector. In order to get this, I redefine this beta and chemical potential to xy, as I explained, such that operator WMZN is counted by the weight xm yn. And after lots of computations, I skip the details and you get this result. And you expand this result in small x, small y, and it starts from 1 plus x plus y, dots, dots, dots. And if you look at the point where m is 2, n is 2, you get number 10. This 10 is precisely what you wanted. So this is the formula. The nice thing is when you look at the formula like this, it's terribly looks terribly complicated because it's a group theoretical quantity, but in the end you can get a function which you can put in mathematical and expand. There are several remarks about these results. First, I was counting, so this Z is the number of generating function of the number of matrices is in SU2 sector. And if you look at this location of the pole, then you get Hagedorn temperature as expected. And if x and y are both non-negative, then x plus y equals 1. So the k equals 1 term gives the first Hagedorn temperature. So first singularity which should equal Hagedorn temperature. Now this quantity can also be written as precystic exponential of single-trace generating function. And this is a well-known fact. I don't really discuss what it is, but there is another rewriting. And this derivation, I don't really discuss what it is, but this derivation is only valid in large n limits. For instance, if I expand it up to cubic order, there is some numbers, 3x squared, x squared, 4x squared, 3x cubed, 4x got y, 4xy to y squared, and 3y cubic. This number totally wrong when you consider U2 gauge theory. So there is some corrections. The corrections are actually known, but the thing is when you put finite n, then there is no Hagedorn transition at finite temperature. And there are two reasoning for doing this. One is this matrix model, no physical reason, which is if you have matrix model with finite degrees of freedom, you can have never sharp phase transition. That's physical reasoning. There is also another mathematical formula called Moriwai formula, which counts the Hilbert Poincare series of GLN invariance. And this point of view is pushed by Hanani and collaborators. There is also a mathematician doing this. And what I like is that Mauch contour integral on some space of some characters. And then after doing lots of contour integrals, you get some rational function of x1, y. And you look at this location of the pole on the xy, you find that there is no pole unless x hits 1 or y hits 1. And if you parameterize x and y as exponential minus beta, x equals 1 means beta is 0, which is infinite temperature. So that's what you can see by mathematics. But I have some, I don't know, some question because in string theory, the density of states usually grows exponentially. For instance, in flat space, TH is given by some definite formula. But on the other hand, this tree-level formula of n equals also per mu suggests there is no transition. So this TH should scale non-trivially as a function of NC, or maybe the reason, the thing I truncated to the scalar sector may be wrong. At this point, I don't know how to define which is the real solution to this, and I don't know, maybe if you can.
I'm not sure I understand that. So what you're saying is that at finite ends, there's no Hagedorn transition.
At finite temperature.
Yeah, that's perfectly fine. And then you want to say that the Hagedorn temperature should depend on n in some way so that
no, because
goes
you
away?
see, because you see, I want to take about ADS-CFT and want to extend it at finite n. Now, in string theory, the legend is that density of states exponentially with respect to, well, anyway, in string theory there are many infinite density of states, so at some point the entropy grows.
If you are only looking at a subsector, right? Why do you expect any given arbitrary subsector that you choose to have a growth exponential?
Well, but you see, even in truncation is related to this, how to choose this theory-dependent function theta.
Is there a path integral which computes the thing that you are computing? Meaning what you are doing is you are choosing a subsector over the Hilbert space and trying to sum over it. Is there a path integral that you can write down which will compute this quantity?
No, I'm not saying. No, I'm not saying. If you want to do ADS-CFT, you want to study a general PS224.
Right.
My question is whether if you do PS224, this path integral, including all Topos-Kaplan dependence here, then do you still find Hagedorn transition? This looks like a still finite size matrix model integral. On the other hand, from a spectral point of view, I start including lots of many operators like this. And from string theory point of view, you start including lots of GS collections and GS collections, and then this TH can depend on GS. So my subtlety here is, if you have string theory at finite GS, do you have Hagedorn transition or not? In other words, the density of states grows exponentially.
I think the answer is no. Right. But you would have a crossover. I think this is very similar to ordinary phase transitions. Take the Ising model. So in infinite volume, it has a phase transition at some critical temperature, as is well known. Now, if you go to finite volume, which here would be the same as going to finite n. If you go to finite volume, the Ising model no longer has a phase transition.
No, but Ising model.
Crossover.
But the thing is, Ising model fundamental degrees of freedom are already discrete. String theory, the fundamental degrees of freedom are already string, which is very highly continuous. So what you have to say that this highly degree of freedom should...
we know that the Hagedorn phase transition is a large n phase transition.
That's right.
So it comes from a saddle point that you have at large n.
That's right.
If you go to finite n, you can do numerics. People have done numerics, I think, on that.
No, the thing is...
It's a crossover. So it becomes, it's no longer a sharp phase transition, but you get some sort of crossover. It's a very similar effect. I'm not saying it's the same physically, but mathematically it's the same.
The thing is, what the point of view you're pushing is from gauge theory point of view to me. From string theory point of view, it is totally non-trivial, and in order to say something, you have to assume ADS-CFT, and which is not clear to me. So to me, this is trivial, non-trivial.
But then I can also answer that. So this comes because when you have finite, why do you get from sharp to crossover? From the gauge theory point of view, it comes from the fact that you get relations between operators.
Yeah.
It's well known, like, if you have an n by n matrix, the simple example is if you take trace of x to some high power, which is
Yeah.
higher than n, then
Yeah.
it's well known it's related to the lower order powers.
Yeah, that's what I
So
explained.
at infinite n, these sort of relations you don't see. But at finite n, you have these relations. In string theory, it means that if you're at finite GS, it's like you have some stringy exclusion principle, if you like. You can no longer put, very, very long operators, which will be, putting strings more and more and more and more strings. That you cannot do eventually, because we know that the state you will produce is related to other states with less strings. Of course, this you can never see in string perturbation theory.
I think you still assume ADS-CFT because that's the point. I mean, if you assume ADS-CFT, I can support your argument, but if you start doubting if ADS-CFT is true or not, finite n, I don't think it's convincing.
You're right. I mean, the point is that the only non-perturbative definition of string theory that I know that allows to go to finite GS is ADS-CFT.
Yeah.
So that's why, otherwise you really don't know what it means to go to finite G string.
Yeah.
So.
Okay, maybe you can try to do some numerical simulations in future. Now I want to discuss one loop dimensions. Okay, now I want to start from some explaining notations. Now I want to compute the one loop corrections to partition function, a small lambda. I expanded this. For whose coupling dependence comes from the dilatation. And the first coefficient, Z2, is sum over this mixing dilatation operator one loop. And I rewrite it under some coefficient capital M2 and times some sum over fugacities. And this coefficient is the sum of one loop dimensions over all matrices at fixed charges M and N. And you have to sum over them. Now, this dilatation operator can be given by this operator type formalism, and then if you add this D to some operator O alpha, I define a one loop mixing matrix in this way. This mixing matrix can be represented in permutation basis using the language of permutation groups. Here I introduce this double bracket I and I alpha j. This double bracket ij means it's a usual permutation if I and j is not equal. And if they are equal, it gives me just a power nc. So nc dependence comes from here. And I also have this summation over mu. Mu is the gauge degrees of freedom or redundancy when you specify multi-race operator. So you have to pick up one particular equivalence class, a representative from the equivalence class. So this is the formula. And you want to count, you want to take the trace of mixing matrix, which is putting this both beta and alpha to be the same. Now what I want to do is solve this delta function constraints. But let's look at this last factor, which is double bracket. If you look at each term, then each term consists of mostly even number of permutations, except for the last one. And if you count the parity of permutations, any of power of transposition can become identity. This is actually wrong when MC is finite, but I'm taking larger limits, so it's okay. Then this factor or this permutation must be identity in order to solve this delta function constraint. So this gives me a 2 delta function constraint plus a factor of MC. In other words, only the order MC term survives at one loop. So I divide it into 2 delta functions and put MC. So this is a formula for the sum of one loop dimensions. And the next thing is you want to compute this coefficients. Okay, the final thing I want to compute is a generating function. And this coefficient is given by this. There are 2 terms. The first term, which is almost conjugation. The second term is conjugation and ij. And the first term, second term are related by replacing this mu by another or another factor mu naught, which is defined by mu ij times mu. And I compute this quantity in two ways. The first one is by taking alpha to be a general element of SL. The second way is restricting alpha to be the single trace operators. Okay, whichever done, the strategy is the same, so I just want to explain how to compute these two terms. The first term is easier. In order to solve the solution of the first term, you have to compute what is the number of solutions to this. The strategy is to pick up this mu, and I specify cycle type of mu to some particular numbers, a set of numbers. And then there is sum of I and j, and I have to specify whether I and j belong to mu, which cycles of mu these I and j belong to. And after that, I have to solve two delta function constraints simultaneously. And I can choose some particular parameterization of mu and this alpha inverse mu inverse alpha. But the basic technique is there's this conjugation identity where you put where you have some permutation conjugated by alpha is alpha acting inside this cycle decompositions. And you can count what is the redundancy in this description. The second term can be proceeded in the same way, with the difference that now you have to look at mu not instead of mu. So there's an extra complication because I choose mu. I choose a cycle type mu as some particular numbers, set of numbers. Then I define I and j where these numbers depend on mu. After that, I have to generate various mu nodes, and this mu node is the one which I have to solve in this delta function constraints. Anyway, things are a little bit complicated, and after some computation, you get some numbers. And this is the first results, where you compute all multi-trace operators. And here I introduce heaviside theta functions on discrete variables, where this theta is 1, with x is greater than 0, and theta is 0 when x is non-positive. Anyway, you get some numbers, and this sum has to be sum over all possible partitions of and L start from 0 to infinity. Now, as I said, I can do the same calculation using the single trace restrictions. And there is a similar formula. But then the claim is that single trace partition generating function is related to the multi-trace partition function by precisive exponential. The second form looks much nicer than this previous page, this results, because if you restrict this result to the case where x equals y, then I can reproduce no results by using a Fourier theorem which was done by Spradenborowicz in 2004. Now, this agreement is partition. The first result and second results are quite non-trivial to me because I couldn't prove it directly. But if you expand both sides, and you can really find actual numbers. For instance, 6 comes through one loop, conic dimensions, and 10 comes from another sum of one loop dimensions and something else, and it continues. Okay, so I got some nice formulas, and then I want to compare it with integrability predictions. I can do this integrability prediction because, as you know, n equals for super MUs is integrable at large n limit. In particular, in SU2 sector, this is related to the XXX 1/2 spin chain with level matching condition. So this is called beta density equation. This is called level matching equation. Now, this complete list of solutions of XXX model can be described by the so-called extended Q system. the extended Q system is some functional equation defined on the Young tableau. And in order to describe impose it, you have to write down this equation, where QAS of U is a polynomial of U of degree, some fixed degree I'm going to explain. Then this plus or minus is a shift of rapidity U into plus I half or minus I half. For instance, this is one simple example of extended Q system. I first write down representation of SU2, which is a Young diagram L boxes on this AS plane. And I put the numbers at each node. And this number is, it's not hook length because you have to count all the number of boxes to the right and to the top. But sometimes it's hook length. Okay, now you have polynomials, and I specify polynomial degrees, and I give you this functional equations, and there's a boundary condition which is trivial on this side. And now you can solve all the Q system equations. And you get, after doing this, you get energy which is related to this Q function at position 1, 0. And if you take logarithmic derivative and you get energy, that's the strategy. Of course, the point is when you try to solve this lots of polynomial equations, you find actually lots of solutions. And this method, in principle, gives you all the solutions, but it's not explicit enough to me. So I want to compare the two results. Before doing that, I have two questions about Q system. First of all, I have to impose a level matching condition. But the Q system, in principle, you can lift this level matching condition and try to solve, try to find the solution, all the solutions, which is more appropriate in condensed matter equation, condensed matter physics. And also, there are so-called exceptional solutions, which should be regularized by twist. The exceptional solutions have the solutions which are beta roots at U equals I half or minus I half, in which this logarithmic derivative are apparently singular. And then you can go finding the computing energies. And there's another caution about comparison, because here I started from single trace, I generated merge trace, and I find all possible sum over merge trace operators. On the other hand, Mandelstam equations with regular beta roots only describe the SU2 highest wave states. So I have to multiply the SU2 multiplicity for each set of solutions. So this is the somewhat complicated part. But if you take small n, and do some list of numbers, you can really do comparison. For instance, the left table is result from permutation basis. The right table is result from Q system. For instance, this 2, which is conical dimensions, which they match. This 2, 3 doesn't match, but you can see that 10 is 6 plus 5. So 10 comes from descendants, and there's another state with dimension 4. So that's why I'm taking 10 here. And the things carries on in a similar way, and you can find some perfect agreement, at least for the numbers I described here. But there is some complication related to this part. Maybe it's nice to have a similar analytic formula for this beta system, but I'm not sure if such equation exists. How many minutes do I have?
So about 15.
50.
15, 1 5.
50.
Yeah.
Okay. Well, actually, I'm going to end conclusion, but I can show some plot about level matching, Hagedorn temperatures. Okay, what I want to do is to show some plot, but before doing the plot, I have to explain something. So I was computing this grand partition function weak coupling, and I found that this x and y has some pole where 1 minus xk minus xyk is 0. And I rewrite x and y by taking off this exponential part. So this is purely dependence on the S1 radius, and the rest is a fugacity coming from the chemical potential. Now, in terms of this beta, you can easily find that these poles living at this position, k divided by log of x theta k plus y theta k. Now, this pole, since I'm taking a most general chemical potential, which can be complex, there is no reason that you can find this tk star on the real axis. So you can choose do some play around in the plots. So by definition, Hagedorn temperature should be the smallest value of this T star k, the location pole, which lies on the real axis. For instance, in the k equals 1 case, this can be the smallest value when both x and y are positive and x plus y is greater than 1. However, if one of them x or one of them y are negative, and then still x square plus y square is positive, then k equals 2 is actually the smallest. And I can do this argument. For instance, in the first case, where k equals 1 is the smallest, Hagedorn temperature is given by this formula, which is well known. But I can go to some second branch where the Hagedorn transition goes a little bit farther from the usual one, and still the right carry on computation to get one loop corrections. Here is some plot. This plot is three-dimensional plot where the z-axis is basically the free energy, and this x and y are rescaled fugacities. On the left-hand side, you see where the cases where x and y are real. So what you find here is some symmetric distribution where you can put x to minus x, y to minus y. You still find same. This is a plot in fixed temperature, and I plotted same x. So on the right hand side, we plot on the axis x equals y. So some x can be negative. So what I want to say is that there are two branches where x is positive. Then this is the region where the first pole starts to diverge. You can see the divergence because the plots are really discrete. This is the second branch, which is slightly towards higher temperature. But this is the point where the divergence occurs on the second pole. Maybe this is the only numerical simulation I did in this talk. That's what I want to show. Now I want to conclude. So in this talk, I explained permutation basis of operators, and then reviewed some tree-level counting formula, and then I started describing the sum of one loop dimensions and show the plot about Hagedorn temperature. The outlook is to go to higher loop orders. Higher loop orders becomes important because Wadawara corrections can be non-trivial. At one loop, there's only one term, which is exactly the same as planar contribution. But starting from two loops, there will be 1 over n squared term. Another point is go to larger sector, like PSU2/4. To do this, permutation basis is not really efficient method. But there's an integrability method called Hagedorn temperature, TBA. This TBA describes the dependence of Hagedorn temperature at large n, but it doesn't give the partition function itself. This method is developed by Armac and Willem last year, and you may be able to introduce scalar potential in general ways. Finally, another motivation is to take OP limit of 4-point functions. This is another variation where you want sum over all possible base under solutions. Again, from integrability methods, you know how to do this. Some algorithm is known, but there is no cross formula for doing this type of questions. So thank you for your attention.
But there's certainly time for some questions. If not, yeah, there is.
One more. So with the Young diagrams that you study, it doesn't matter that they're inverted, so that the subsequent rows are larger than the higher rows.
Is it this or is it another Young diagram?
No, this one.
Oh, this one is just representation of global symmetry. So there's no M here. It's up to, for instance, this is SU2 Young diagram. So the rows is, row is, okay, A goes up to 2. You cannot go 3 because this is antisymmetrization by SU2.
Yeah, yeah. So it doesn't matter that, so you don't necessarily have to have the higher rows being longer than the more. Okay. So the lower rows should not be longer than the higher rows. That doesn't matter in this particular case.
No, the motivation of doing Young diagram is I want to classify as states depending on the SU2 global representation of the global symmetry. So this is one efficient way of doing this, and you don't need to consider more rows. It just extends in this direction.
Any other questions? If not, let's thank you again.